Greetings everyone, this is Mr. Mullen, and today I'm doing a podcast going through energy homework number 3. I'm going to go through a couple examples so I can give you a work through of a couple of these problems so that you'll be more successful at this worksheet. Notice at the top of the worksheet, feel free to pause this video and take a look at all those equations relating the different types of energy we've looked at, including the types of units that you should have when you get to the end. Alright, so we're going to go ahead and get started with question number 3. And question number 3 says a 0.4 kilogram block is placed on a spring and compressed 0.20 meters. And so if I look at this picture over here, it gives me the displacement and the spring constant of that spring. After it's released, to what maximum height does the block reach? Okay, so we're basically looking for how much our vertical height has changed. How fast was the block moving when it was at half its max height? And so we're looking for how fast velocity is equal to question mark, and this is going to be at basically 1/2 of that max height, that change in position. So when I look at this here, you can include what's in your system. So I'm going to include the block. I'm going to include the spring so that I can keep all of that elastic potential energy within my system. And then I'm going to include the earth. And so now that I've included my system, let's look at what types of energy are present. And so it's not moving. Now GPE, it's obviously from the ground. However, I can choose where y is equal to 0. So I'm going to make my problem a little bit easier, and I'm going to make y equals 0 at the bottom of the spring. And because energy is conserved, even if this spring shoots up the block and it comes back down again, it's never going to get more elastic potential energy than it currently has. So it's never going to go below that mark. So there's our initial position. And so I'm going to say there's no GPE. Elastic potential energy, lots of that, and I haven't dissipated any yet. So I'm just going to go ahead and give this thing, say, 4 blocks of elastic potential energy to start with. Afterwards, I look at my final situation up at the top. It has come to rest. Now some of that energy has been transferred into the gravitational field of the Earth. The spring has sprung. I'm going to ignore drag or air resistance for this type of problem because it's going to be difficult to calculate that. But I'm going to go ahead and transfer then all my blocks into 1, 2, 3, and I gave a little bit too much. 4. Okay, so there's our energy. Oh, I do need the other one. So what I'm going to do now is I'm going to make an equation relating the quantities of energy involved. And so simply I can do that. We have the elastic potential energy of the spring was equal to, there were no energy transferred in or out through work, and so that means that we had left our GPE. And so I'm going to rewrite now EP is equal to GPE using how I can calculate each of those. So when I look at elastic potential energy, this is just 1/2 k delta x squared, and that's equal to GPE, which is just equal to m times g times my delta y. Now what I like to do is I like to rearrange this equation here and then plug in numbers. Sometimes when you do that, especially when you're dealing with kinetic energy and GPE, you're going to find that variables will cancel out. Now in this case, none of these things will cancel, but sometimes you can get rid of mass completely. So I'm going to go ahead and rearrange this and then plug in afterwards. So I'm going to get delta y by itself, divide both sides by mg, so those cancel, divide this side by mg. And so now I have what delta y is equal to. So my delta y is equal to 1/2 my spring constant k, which was, I look at the problem over here, 320 newtons per meter. And that's all multiplied by delta x squared. The spring's displacement was 0.20, and we're going to square it. And that's all divided by mg. I look at the mass given in the problem, 0.4 kilograms, and that's times my gravitational field strength of 10 newtons per kilogram. Unit-wise, we should be left with a unit of distance. Don't forget my meters there. Okay, so meters cancels meters. One of those meters cancels. Let me just redo this. Okay, so this meter cancels with one of those meters. This newton down here cancels with that newton up there. This kilogram cancels with that kilogram. And so you're left with meters, and that's right. So our delta y is going to be equal to 1.6 meters is going to be our change of position. And so we're going to go ahead and say that we made it 1.6 meters from the starting point. I don't know how far it is off the ground, but that doesn't matter. All right, so the next step is, it says, how fast was the block moving when it was at half its max height? And so what we can do now is we can say, okay, well, it made it 1.6, but I want to know how fast it was moving, so we're looking for the velocity when it was 0.8 meters high. Okay, half the max height. So I'm going to turn my LOL diagram into an LOLL diagram. The system hasn't changed, so I don't need to do an LOL-OL diagram, so I'm just going to draw this new one here. And we have our KE, GPE, EPE, and EDIS. So we're going to look at our energy types. I'm going to say there was no energy dissipated. The spring is still already sprung. But GPE now, because it's halfway up, is going to be less. And KE is going to be some because it's going to be moving. So because it's exactly halfway up, and looking at my equation for energy gravitational potential, these are all direct relationships. So if I'm half as high, then the energy is going to be half as much. So I'm going to use 2 blocks and 2 blocks. And so now I'm going to make a new energy expression, okay, for my part 2 here, and that shows that the EPE is equal to the KE plus the GPE when it's halfway up. And so now I need to write a new expression. Now you may, depending on how you solve this problem, you may have already solved for the EPE earlier. I'm just going to go ahead and plug in my whole expression here. 1/2 K delta X squared is equal to, my kinetic energy is 1/2 mv squared, and then that's plus mg delta h. Now I could rearrange and solve for my velocity here, or I can plug in numbers and then rearrange. I'm going to do the second method now. I'm going to plug in numbers and then rearrange. And so I'm just going to go through and start plugging in numbers. 1/2 K was 320 newtons per meter times delta X squared, 0.20 meters. That's squared. And that's all equal to 1/2. My mass was 0.4 kilograms times v squared. And that's plus mg delta h. My mass is 0.4 kilograms times my 10 newtons per kilogram. And that's all times my delta h, which with this case we went half as high. Don't forget that. Now we're at 0.8 meters. We went half the height. So this is a big expression. I'm going to simplify my life and reduce some of these things down. This first term is going to reduce down to 6.4 newtons times meters. Okay, so 6.4 joules. The last term is going to simplify down to 3.2 newtons times meters, or joules. And then this other term is going to be equal to 0.2, and then we'll still have that kilogram hanging out, times v squared. So I rearrange this, I subtract, this is plus, subtract 3.2 from both sides. I'm going to get 3.2 joules is equal to 0.2 kg v squared. When I divide both sides by kg, we're going to get our v squared is equal to 16. And there's going to be a bunch of units on there, and I could break down joule and all the units would work out. But basically when you get to the very end of this thing, our final velocity is going to be equal to 4 unit of meters per second. The units do work. And so there's our final velocity. And so we were able to solve for this other situation using this expression. I also want to do for you number 11, just to kind of give you another look at how you might solve one of these problems. Number 11 is involving a cart that's being pulled at a constant speed, 100 kilogram crate. Now it gives me the coefficient of friction, and that's going to be our mu, and that's equal to 0.20. And then it says it's moving over a distance of 2.5 meters. So there's our little delta x. And it's asking how much energy did we dissipate through friction? How much energy was dissipated? And then the second question says how much work was done by the crate, on the crate, by the motor. All right, so clearly the motor is exerting a force over a distance here. And so as it's pulling, it's doing work on the block, and at the same time, the block is grinding across the ground, and all that work that it's doing is being dissipated by friction. So I get to the end. So let's take a look at our system here. We have dissipated energy, so I'm going to go ahead and say our block's in there, and the ground is in there because it's definitely friction is present. No vertical displacement, so we're not going to worry about that. I'm going to keep the motor outside the system because I'm not going to be worried about its energy situation. I'm just going to be concerned with the block. So here's my motor. So beforehand it says the block is moving, so it does have a little piece of kinetic. There's no GP, it's on the ground, there's no springs, and I'm going to start with a fresh energy situation, so I'm going to look and say there's no dissipated energy. Now afterwards, I notice that it's still moving, so I still have a little tiny block of KE. It's still moving. It's still on the ground, there's still no springs or anything, but as I've grounded across the ground and all this friction's going on, we're going to dissipate a bunch of energy. So where does that energy come from? It has to come from somewhere. So this is where our motor, as it's doing work onto the system, how much energy is going to be done by the motor? Well, whatever I need. So 1, 2, 3, 4. There's all the work done by the motor coming into the system. How is the motor doing work? It's exerting a force. In this case, it's tension. And it's exerting that force over my little delta x. So I can figure out that. So there's my motor doing some work on my system, and now we can account for the amount of energy done. Okay, so when I look at my energy equation, we can very reasonably say, well, it's KE plus the work done is equal to KE plus the amount of energy dissipated. What's nice about an equation is because KE doesn't change, I don't have to worry about it in my energy equation, because if I subtract KE from both sides, it disappears. And so we can really cross these out, the same on both sides, and simplify this and just say that our work is equal to our dissipated energy. And so this question asks for how much energy was dissipated and how much work, so we're going to do 2 for 1. So when I look for what was the amount of energy dissipated by friction, or the work in this case, we're going to need to figure out the force of friction and how long that force of friction was acting. So, force of friction, I'm going to go back and remember, to figure out the force of friction, I need to know how hard the surfaces are pressed together, the normal force, and how sticky the surfaces are. So I look at my 100 kilogram crate box, and if I wanted to figure out, what is the normal force on that? Take 100 kilograms times my 10 newtons per kilogram. We have a 1,000 Newton crate. So normal force is 1,000 newtons. So I'm going to go ahead and break down my force of friction into the coefficient of friction times the normal force. And so when I go to all this, we're going to go ahead and rearrange this and plug in 0.20 is my coefficient of friction times 1,000 newtons, all times my 2.5 meters. And when I plug all those things in, we're going to get an answer of 500 joules, 500 newtons times meters.